When the big box on the right collides with the little box on the left, each box experiences a force that is equal in magnitude but opposite in direction. This principle is proposed by Isaac Newton in his third law of motion. From this law, we can derive another important law of physics called the conservation of momentum, which is the topic of this presentation. Since F equals ma and acceleration is the change in velocity per unit time, we can cross out the contact time and see that the momentum gained by one object equals the momentum lost by the other. This shows that the total momentum before an interaction always equals the total momentum after. Remember, momentum is mass times velocity. This is definitely worth repeating. In a closed system, when two objects interact, the sum of their momenta before the interaction equals the sum of their momenta after the interaction. Since momentum is mass times velocity, this is the mathematical expression for the law of conservation of momentum. When the fish on the left swallows the fish on the right, it slows down. Notice that the momentum of the large fish is negative and the momentum of the small fish is positive. This is because momentum is a vector and negative and positives are used to indicate direction. The total momentum is negative 4 kilogram meters per second before, so the total momentum after the little fish is, or the big fish eats the little fish, then the total momentum after is negative 4 kilogram meters per second. A 3 kilogram object traveling at 6 meters per second has a perfectly elastic collision with a 4 kilogram object traveling at 8 meters per second. After the collision, the 3 kilogram object will travel 10 meters per second west. What's the total momentum before this collision? So we pull out the information from this question. The m1 is 3 kilograms, its velocity is 6 meters per second. m2 is 4 kilograms, and its velocity is negative 8 meters per second, simply because it's traveling in the westerly direction. So after we write, the 3 kilogram is going west, it's negative 10 meters per second, and the other one, the 4 kilogram, we don't know its velocity. Once again, notice that we made the velocity of the 4 kilogram object negative. This is because it's moving west. Momentum is a vector. Objects moving west are made negative, and objects moving east are positive. Since momentum is the product of mass and velocity, we can calculate the total momentum by summing each object's contributions. The 3 kilogram object has a momentum of 18 kilogram meters per second, and the 4 kilogram object's momentum is negative 32 kilogram meters per second. That total brings us to negative 14 kilogram meters per second, or 14 kilogram meters per second west. Notice if we drop the negative, we then add the direction west. The total momentum before and after this interaction is negative 14 kilogram meters per second, that is, or 14 kilogram meters per second west. Now, what will the velocity of the 4 kilogram object be after this collision? Well, what we do know about after the collision is that the total momentum after is negative 14, so we'll use the conservation of momentum. We can find the velocity of the 4 kilogram object by using the conservation of momentum. Notice once again that the velocity of the 3 kilogram object is negative 10 meters per second. This is because it's traveling west. West is negative and east is positive. When you divide both sides of the equation by 4, we see that the velocity of the 4 kilogram object is 4 meters per second, positive 4 meters per second, that is, or 4 meters per second east. A train with a momentum of negative 30 kilogram meters per second collides and attaches itself to a train with a momentum of positive 15 kilogram meters per second. What would the momentum of these trains be after the collision, since the total momentum before is negative 15 kilogram meters per second? Then the total momentum after would also be negative 15 kilogram meters per second. Let's try another one. Example 2. A 10 kilogram block moves with a velocity of 2 meters per second to the right, okay, that's positive, and collides with a 10 kilogram block B, which is at rest. So that means it has no momentum. After the collision, block A stops moving and block B moves to the right. Find the total momentum after. We know everything about before, and yet they're asking us to find the total momentum after. Since we know the mass and velocity of each object before the collision, we can use that to find the total momentum before, and therefore the total momentum after. Since the 10 kilogram object is at rest before the interaction, it has zero speed and zero momentum. The entire momentum before is positive 20 kilogram meters per second. After the collision, object A stops, so its velocity is zero and its momentum is zero. We can find the speed of object B after the collision by using the law of conservation of momentum. From our previous question, we found that the total momentum before the interaction equaled positive 20 kilogram meters per second. From this equation, we can find that object B has a velocity of 2 meters per second. Example 3. A 10 kilogram cart moving with a velocity of 10 meters per second collides and attaches itself to a 10 kilogram cart moving at a velocity of 50 meters per second west. What is the total momentum before the collision? We begin by underlining and writing down what was given. The first cart, we'll call cart A, has a mass of 10 kilograms, a velocity of 10 meters per second. We made that positive because that's east. But the second cart was also 10, but it was going west, so it's negative 50 meters per second. Since the 10 kilogram object had a velocity of 10 meters per second, its momentum is 100. Since object B had a mass of 10 kilogram at a velocity of negative 50 meters per second, its momentum is negative 500 kilogram meters per second. When you add that all up, it's negative 400 kilogram meters per second. I wrote it with two significant digits as negative 4.0 times 10 to the 2 kilogram meters per second. The second part of this question asks for the total momentum after. So since we know the total momentum before, it's obvious that the total momentum after is negative 400 kilogram meters per second. Now that we know the total momentum before, we can find the velocity of the combined masses after. Once the two 10 kilogram masses combine, we have a single mass of 20 kilograms. The velocity of the 20 kilogram mass after is negative 20 meters per second, or 20 meters per second west. What is the magnitude of the total momentum of these cars before the collision? The momentum of the 4 kilogram cart moving to the right is 12 kilogram meters per second, and the momentum of the 6 kilogram moving to the left is negative 18 kilogram meters per second. When we add these two momenta, we get a total momentum of 6, that is negative 6 kilogram meters per second. We should not be surprised the total momentum is negative because the cart moving to the left had a greater momentum than the cart moving to the right. Here's one more example before we wrap things up here. When these two trains collide, they stop. What must be true about their total momentum before? Well, since they stop, their total momentum after equals 0. This must mean that their total momentum before must have been 0 too. That can only be true if their individual momenta before were equal but opposite. Remember, in all interactions, the total momentum before equals the total momentum after. Individual momentums can change, but not the total. This law is derived from Newton's third law of motion that states that when any object A exerts a force on object B, the forces they exert on each other are equal but opposite. And this is the end of my presentation on the law of conservation of momentum.